This video showcases the final functional CHUMP build. In addition to the eater clock build, program counter, and program EEPROM explored in the last installment, the CHUMP features a control EEPROM, multiplexer, ALU, accumulator, address register, and RAM with supporting inverter. The wires for the build are color-coded into yellow for the program counter and control/program EEPROMs, white for clock, blue for ALU, and green for everything else. LEDs monitor the clock circuit, the instruction line the program is at via the program counter, the operand portion of the instruction, and the output of the accumulator. The AT28C16 used as the control EEPROM stores what are referred to as control codes, indicated on the block diagram by the letter C. There are a set of 8 control codes from the control EEPROM for every instruction. The opcode of the instruction available on the outputs of the program EEPROM connect to the first 4 address pins of the control EEPROM. It then outputs the 8 control codes for each instruction on its output pins. One more control code comes from the low order bit of the opcode, and another comes from ANDing the 2 most significant bits of the opcode. The control codes ensure that each IC behaves as it is supposed to in order for the processor to execute a given instruction. The 74LS157 data selector used as the multiplexer selects whether a constant coming from the operand on the program EEPROM or a value stored in RAM passes through to the B operand of the ALU. The control code it receives comes from the low order bit of the opcode. If it is low, signifying a memory instruction, the constant passes through. If it is high, signifying a memory instruction, the value from RAM passes through. The output of the multiplexer feeds the inputs of the program counter and address register. The SN74LS181 ALU performs arithmetic and logic functions for the processor. It can perform a variety of functions summarized in this table to its A and B operands. The A operand comes from the output of the accumulator, and the B operand comes from the output of the multiplexer. The result of the operation, for example A plus B, is presented on the function output pins of the IC. It receives 6 control codes from the control EEPROM that select the function to be executed. Its A equals B pin, wired with a pull-up resistor, goes high when a branching instruction, either a go-to or a conditional if 0, must be executed, triggering a Z flag. The flag is NANDed with the 2 ANDed most significant bits of the opcode, triggering the NAND gate to output a low, causing the program counter to jump to whatever address is on its input pins from the multiplexer. The 74LS377 octal D flip-flop is used as the accumulator. It transfers whatever it's on its input pins to its outputs after one clock pulse. Its inputs are connected to the output of the ALU, and its outputs are connected to the A operand of the ALU. It receives a control code from the control EEPROM for its active low enable pin. The 74LS174 hex D flip-flop is used as the address register. Its first 4 inputs are connected to the output of the multiplexer, with its outputs connected to the address select lines of RAM. When the clock is pulsed, it transfers the data on its inputs to its outputs. RAM's control code from the control EEPROM is also fed through one of the flip-flops on the address register, allowing it to be clocked so it is in sync with reading from and writing to RAM. Feinberg's sample code is stored on page 0 of the program EEPROM. It places a 2 in the address register, loads the value of RAM address 2 into the accumulator, adds 1 to the accumulator, and then stores that value back to RAM address 2. It then branches back to 0 and repeats over and over again. The custom program is stored on page 1 of the program EEPROM. The first instruction, load 2, places the constant value 2 into the accumulator. The constant comes from the operand portion of the instruction, which is presented on the least significant nibble of the output of the program ROM. It is fed into the 0 input of the multiplexer and passes through to the multiplexer's output, as the control code for the multiplexer, coming from the low order bit of the opcode on the program ROM, is low, signifying a constant instruction. The 2 then passes through the ALU as it performs an F equals B operation based on the 6 control codes it receives from the control ROM. The 2, now sitting on the inputs of the accumulator, passes through to the outputs of the accumulator when the clock is pulsed. Thus, a 2 is now in the accumulator. The second instruction, store to 0, stores the value of the accumulator, 2, into address 0 of RAM. A 0 passes through the multiplexer, as this is another constant instruction, and goes into the input pins of the address register. The read-write control code coming from the control ROM also goes into an input of the address register. It is a 0 as a value is being written to RAM. The 2 from the accumulator is available on the inputs of RAM. When the clock is pulsed, the contents of the accumulator 2 are written to RAM address 0, as it receives the address from the address register and the data from the accumulator. The next instruction, load 5, places a 5 in the accumulator in the same way as described for the value 2. Instruction, store to 1, then stores the 5 to RAM address 1 in the same way as described for the value 2. The next instruction, read 0, places a 0 in the address register. The 0 comes from the operand portion of the program ROM and is passed through the multiplexer. There is now a 0 available in the input pins of the address register. The control code coming from the control ROM to the address register is a 1, as RAM will be read from in the next instruction. When the clock is pulsed, the 0 value is transferred to the outputs of the address register connected to the address select pins of RAM. The next instruction, load it, places the contents of RAM address 0 into the accumulator. The inverted outputs of RAM equal the value in RAM address 0, which is a 2, and are connected to the 1 input of the multiplexer. The value passes through the multiplexer, as this is a memory instruction, and thus the control code coming from the low order bit of the opcode is high. The B operand of the ALU connected to the output of the multiplexer equals the value of RAM address 0 at this point. The function outputs of the ALU connected to the inputs of the accumulator also equal that same value, as an F equals B operation is being performed by the ALU. When the clock is pulsed, the 2 on the outputs of the ALU is transferred to the outputs of the accumulator, and the accumulator now equals 2. The next instruction, read 1, places a 1 in the address register, in the same way as described for the read 0 instruction. The next instruction, add it, adds the contents of RAM address 1 to the accumulator. The inverted contents of RAM address 1, 5, pass through the multiplexer, as this is a memory instruction, and sit on the B input of the ALU. The A input of the ALU equals the contents of the accumulator, 2. The function outputs of the ALU now equal 7, as an F equals A plus B operation is being performed by the ALU based on the control codes coming from the control EEPROM. When the clock is pulsed, the contents of the accumulator equal the function outputs of the ALU, 7. The next instruction, subtract 6, subtracts the constant value 6 from the accumulator. The 6 comes from the operand portion of the output of the program ROM. It passes through the multiplexer, as this is a constant instruction. Thus, the B operand of the ALU now equals 6. The A operand of the ALU, connected to the outputs of the accumulator, now equals 7. The ALU performs an F equals A minus B operation. Thus, its function outputs equal 1. When the clock is pulsed, the accumulator equals 1, as the value on the output of the ALU is transferred to its output. The next instruction, if 0, checks if the contents of the accumulator equal 0. To do this, the control codes dictate that the ALU perform an F equals not A operation. If the contents of the accumulator equal 0, the function outputs of the ALU will all go high. As these are connected to an AND gate which has its output connected to the A equals B pin, the A equals B pin goes high if the contents of the accumulator equal 0. If this were the case, the Z flag, which is the A equals B pin, would go high, triggering a branching instruction. Since this is not the case, the Z flag is low, and the program counter is not triggered to go back to address 0. Thus, the instruction is ignored, and the program counter moves on with the next clock pulse. The next instruction, subtract 1, subtracts the constant value 1 from the accumulator. The 1 comes from the operand portion of the program ROM and passes through the multiplexer, going into the B input of the ALU. The A input of the ALU, connected to the outputs of the accumulator, now equals 1. Based on the control codes from the control ROM, the ALU performs an F equals A minus B operation, and the function outputs of the ALU equals 0. When the clock is pulsed, the data on the outputs of the ALU is transferred to the outputs of the accumulator. Thus, the accumulator now equals 0. Finally, the last instruction is a go to 0 instruction, bringing the program back to address 0 to start again. The 0 from the program ROM goes into the 0 input of the multiplexer and passes through, as this is a constant instruction. The outputs of the multiplexer pass the 0 to the inputs of the program counter. Thus, there is now a 0 sitting on the inputs of the program counter. The two most significant bits of the opcode are fed through an AND gate, which has its output connected to one of the inputs of the NAND gate connected to the program counter's active low load pin. The output of the AND gate represents the control code for the program counter. The output of the AND gate is high, as the two most significant bits of the opcode are high, which is only true for branching instructions. The ALU performs an F equals 1 function based on the control codes it receives, meaning the output of the ALU now equals 15. Thus, the A equals B pin connected to the output of the gate performing an AND operation on the 4 function outputs goes high, and the Z flag is triggered. Thus, the NAND gate has 2 high inputs, one from the AND gate and one from the Z flag. Thus, its outputs go low, triggering the program counter to load the data on its inputs and transfer it to its outputs. Thus, the program counter's output now equals 0, and the program begins once again.